Noether's theorem. So we also discussed the inadequacy of the relativistic quantum mechanics and the unification of special theory of relativity and quantum mechanics. Okay, so we have already seen that the non-relativistic Schrödinger equation is given by E is equal to p square by 2m, and for relativistic particle the energy E square is given by p square plus m square, and we get the Klein-Gordon equation. But here the wave function psi of x comma t is the wave function of a relativistic particle of mass m, and x represents the eigenvalue of the operator x cap. This equation of motion is same as the equation of motion for a simplest classical scalar field theory whose action is given by, okay, so this is for scalar field theory, classical scalar field theory whose action is given by d for x plus m square phi square. Okay, the corresponding equation of motion in this case is similar to the Klein-Gordon equation, but here phi is a classical field, okay, and x is a position in space. So here you can treat both space and time on equal footing, but in relativistic quantum mechanics you cannot do that because x is the eigenvalue of the operator x cap. So even though the equations look similar, they have different interpretations. And also in the last class we have seen the difficulties, okay, difficulties of unifying the special theory of relativity and quantum mechanics. So the first difficulty was that a positive definitive probability density cannot be defined because there is no sensible way to define the probability density, and if you want to interpret a wave equation then you need a probability density. So probability density was the first difficulty, right? And the second, presence of the negative energy states. If E square is equal to p square plus m square, then energy can take negative states, so which cannot be avoided in quantum mechanics, right? So negative energy. And the third difficulty was that number of particles are fixed. Particle number cannot change, and in relativistic system the number of particles is not conserved. There is continuous annihilation and creation of particles. Therefore in this way we cannot unify special theory of relativity and quantum mechanics. Okay, so all these difficulties say that this kind of wave equation cannot be a fundamental description of relativistic quantum mechanics, and therefore we need a quantum field theory to address these difficulties. So what is the proper way to describe a relativistic particle using quantum mechanics? So the proper way to describe the quantum mechanics of a relativistic particle is to start with the classical field theory and then quantize it. So you can first start with a classical scalar field theory and then quantize it. So we will see that it will automatically gives a formalism for treating arbitrary number of particles. So in field theory both x and t are parameters, right? Because x is position in space and t is time, so both are parameters, and they are on equal footing as required by the special theory of relativity. Okay, so next we'll go to field theory as a limit of discrete system. Now imagine some particles, for example atoms, that are connected by springs to form an infinite chain. Okay, so you have to imagine some particles, for example atoms, it can be atoms, okay, which are connected to each other by a spring. The spacing between two atoms, let it be a. Okay, each particle has an initial position which is x0, x1, x2, x3, etc. Okay, so the initial position of the particles can be labeled, and let the deviation of the, so like that you have n number of particle. Okay, this is a continuous chain and you have n number of particle, and let the deviation of the nth particle from its equilibrium position be given by eta. Okay, so eta is the deviation, and deviation of the nth particle is given by eta n, and that will be the deviation from the equilibrium position. Okay, right. Now we have to write the Lagrangian for this system. So Lagrangian is given by kinetic energy minus potential energy. So you have n number of particles, right? Therefore the kinetic energy will be the summation over n half, okay, let mu be the mass of each atom or each particle, then I'll have half mu eta n dot square. Okay, this will be the kinetic energy. And if you see here, there will be two type of potential. First potential will arise due to the interaction between the neighboring particles, and the harmonic potential of the each particle, that will be the second potential. So let's write the summation will be implied for all the particles. So lambda by 2 eta n plus 1 minus eta n whole square minus half sigma eta n square. So the first term is the kinetic energy of the particles. So let's assume that each particle has a same mass mu. Okay, therefore this term will represent the kinetic energy, and the second term represents the interaction between the neighboring particles. And the last term represents the harmonic potential of each particle. All right. Yeah. Now I want to write the Lagrangian in terms of the lattice spacing A. Okay. Therefore, I take A outside. So if I take A outside, then in the remaining terms, you can see half mu by A eta n dot square, right, minus, then I have to write multiply and divide by A square, because, and one A I am taking outside, so I'll write only A. here I'll get eta n plus 1 minus eta n by 2 whole square, and minus the last term will be sigma by a eta n square. So now I have, in terms of the lattice spacing, I have multiplied and divided by a, and I have taken a common outside. Fine. Now here I can define the mu by a as mu tilde and lambda a in the second term as lambda tilde and sigma by a in the last term as sigma tilde. So this is nothing but rescaling. So I have rescaled the parameters in terms of the lattice spacing. Fine. So now if you look at this system from far enough distance, okay, far enough distance in the sense x must be very much greater than a. If x is very much greater than a, which means that I am looking at this system from a large distance, so much large such that the distance is very much higher than the lattice spacing itself, then in that case it behaves as a particle continuum. So I cannot see this as a harmonic oscillator, but I can see this as a continuum of particles if I look at this from a very large distance. Okay, and in that case the lattice spacing a will tend to 0. If I look at this object from this system from far enough space, then it behaves as a particle continuum such that the lattice spacing will tend to 0. Okay, and not only that, for a continuum of particles, the summation or a multiplied by the summation can be replaced by integral dx, because it's no more discrete but it is continuous. So I can replace a summation, a multiplied by summation, with integral dx. In that case the Lagrangian becomes integral dx. So now I am replacing a multiplied by summation with integral dx, and I'll write the rest of the terms. It will be half mu tilde eta n dot square minus lambda tilde by 2 eta n plus 1 minus eta n by a whole square minus half sigma tilde eta n square. And also one more thing you have to note here is that now eta n is now eta n x of t, because you are viewing at it from a distance x. So x is also now a parameter here. Okay, fine. Now here I'll take mu tilde common outside, then I'll get integral dx half eta n dot square minus lambda tilde by 2 mu tilde eta n plus 1 minus eta n by a whole square minus half sigma tilde by mu tilde eta n square. And here I write the lambda tilde by mu tilde as some w square and sigma tilde by mu tilde as m square. In that case, my Lagrangian becomes mu tilde integral dx half eta n dot square minus w square by 2 eta n plus 1 minus eta n by a whole square minus half m square eta n square. Okay. If I put w square is equal to 1, then the above equation is same as our equation of motion, right? Equation of motion for a relativistic system. So for other values of w, if this is for w equal to 1, for other values of w, so this is for w equal to 1, and if w is not equal to 1, then this is a general equation for non-relativistic system. If w equal to 1, this is for relativistic system, and for other values of w, this is a general equation for non-relativistic system. So if you choose specific parameters, then you can get the relativistic limit. Good. So the simplest scalar field theory describes a spinless and free massive particle, right? But we need a theory that includes interactions and particles with spin, for example electron, etc. Therefore, quantizing the Maxwell's theory, we get free massless spin 1 particles called photon, and combining electron plus photon plus interaction between them, then we reach quantum electrodynamics. So that will be the path that will be following in this course. Okay. Next we will see the quantization of harmonic oscillator in Heisenberg picture. Okay, so this we will be dealing with the free scalar field theories. So free in the sense the particles do not interact with each other, so the interaction term will be absent. In that case, the Lagrangian can be written as half x dot square minus half x square. Okay, and the momentum density will be, sorry, the canonical momentum will be x dot, and the Hamiltonian will be p square by 2 plus half omega square x square, and the equation of motion will be x double dot plus omega square x is equal to 0. So this is important because you can have a classical solution to this equation of motion, and the general form of the equation can be written as x of t is equal to a cos omega t plus b sin omega t. This is the general solution, and in the complex form I can write it as 1 by root of 2 omega a e raised to minus I omega t plus a star e raised to I omega t. So the cos and sine I can write it in terms of exponential. Okay, and this root of 2 omega factor comes from applying the boundary conditions. Fine. And here capital A, capital B, A and A star are all integration constant. Fine. So this is a classical solution. Okay. this is classical solution for the equation of motion. If I want to convert it into quantum, then the position x of t has to be considered as an operator. Okay, that is in quantum mechanics. Then the equation of motion will also become an operator equation, right? That is something like this. Now the quantum mechanical solution of the equation of motion will be cos omega t plus b cap sin omega t. And in the complex form, I can write it as 1 by root of 2 omega a cap e raised to minus I omega t plus, now in quantum mechanics, a star will be a dagger. So I can write a dagger e raised to I omega t. Okay, so a will be operator a cap and a star will be operator a dagger, and p of t is the canonical momentum which we have already obtained here. It is x dot. X dot, in the sense I can write it as dot t x, that is dot t of x cap. So if x cap is this, then first derivative with respect to time I can obtain the momentum operator. So that will be 1 by root of 2 omega a cap. Now differential of e raised to minus I omega t will be e raised to minus I omega multiplied by minus I omega plus a dagger e raised to I omega t multiplied by I omega. Okay, so in general I can write as, so omega by root of omega will be root of omega by 2, and I can take minus I outside. Therefore a cap e raised to minus I omega t minus a dagger e raised to I omega t. Okay, so this will be the momentum operator. So once you get both the position and momentum operator, the next step is to impose the canonical quantization condition. So next we will impose canonical quantization condition. So we know that x of t, p of t, commutator is equal to I. Okay, which means that I have to substitute, right? 1 by root 2 omega a e raised to minus I omega t plus a dagger e raised to I omega t and minus I omega by 2 a e raised to minus I omega t minus a dagger e raised to I omega t. The commutator must be equal to I. So let me solve this one. So from here I can take out the constants. So 1 by root of 2 omega from here and minus I root of omega by 2 from the second term, then I'll get commutator of a e raised to minus I omega t plus a cap dagger e raised to I omega t and e raised to minus I omega t minus a dagger e raised to I omega t must be equal to I. Now I can cancel I from both the sides. Okay, then I will get, and omega, root omega also I can cancel. Root 2 will be 2. So minus 1 by 2 a cap e raised to minus I omega t with a cap e raised to minus I omega t, then plus a cap and minus a dagger, so it will be minus a cap e raised to minus I omega t and a dagger e raised to I omega t. Then next, second and first term, so that will be a dagger e raised to I omega t and e raised to minus I omega t. Next one will be again minus a dagger e raised to I omega t and a dagger e raised to I omega t. So now this will be equal to 1. Okay, and we can see that a comma a will be 0 and a dagger comma a dagger commutation will be 0. Then what is left? I have minus 1 by 2 minus, I can take out e raised to minus I omega t and e raised to I omega t. Then a cap a dagger is remaining here, and in the next term I can take out e raised to I omega t and e raised to minus I omega t. Then the remaining term is a dagger a. Okay, now this is equal to 1. So e raised to minus I omega t and e raised to I omega t will cancel in both the terms. Therefore the remaining term will be minus 1 by 2 minus a dagger plus a dagger a is equal to 1. So the first term is a dagger, fine. So second term is a dagger comma a. So I can write a dagger comma a as minus of a dagger. Okay, so I have minus 1 by 2 minus a dagger is equal to 1. Now the minus I can take outside, so that it will be 1 by 2 times a dagger is equal to 1. So the 2 will get cancelled, and finally I'll get a dagger commutator is equal to 1. So by imposing canonical quantization conditions, it will give the commutators between the new constant operators. Okay, imposing canonical quantization condition will give the commutator relation between the new constant operators. Okay, so here A and A dagger are the new constant operators, and canonical quantization condition is the already known commutation relation between X and P. So if you impose already known the standard or the canonical quantization condition, then we can get a relation, commutator relation between the new constant operators. So I got the constant operators from the constant of integration from in the general solution. Okay, and then they were promoted to the quantum mechanical operators, and to get a relation between this new constant quantum mechanical operators A and A dagger, I have to impose the already known standard canonical quantization condition, and I get the new relation, or the relation between the new constant operators. Fine. So here A and A dagger are the creation and annihilation operators. So the creation and annihilation operators are the building block of the Hilbert space. That is, if you already identify the lowest state, right, then you can, any higher state can be built from the ground state by using the creating operator, right? So if you use the annihilation operator in the lowest state, you will get 0, and to build any state from the lowest energy state, I have to operate with the creation operator, right? So nth state can be obtained by acting the creation operator n times on the lowest energy state. Okay, so this is how you build the entire Hilbert space from the creation and annihilation operators. So what are the general steps? So this is just in the case of a free scalar field theory, right? So this can be applied to any other case. So this is just for a harmonic oscillator in the Heisenberg picture, right? Just for a harmonic oscillator in a free scalar field theory. So if I want to convert other systems into quantum field theory, then what are the general steps that I have to follow? The first step is to write down the general solution. So that was the first step that we have taken, the general solution to the equation of motion. Write down the general solution to the equation of motion. And then we have identified the integration constant and promote the integration constant to a constant operator. If you have more than one integration constant, then you can promote all of them into constant operators. And third step is to impose canonical quantization condition. And finally, use the constant operators to generate the Hilbert space. The same strategy can be applied to any system in field theory. Okay, so for today I think this is enough. We'll see the rest of the portion in the next class.